Put something on.
Something. Yeah, it's 2%. Yeah, must 2%. Karne ni mbovu. You're not seeing shit? Good afternoon. Good afternoon. Hey. Okay, thank you for availing yourself for today's class. We are going to start. It's 12 o'clock. And I will encourage these people who are not using the university email system to join the meeting to start doing so, because as we go on, we are not going to admit you into the meeting. We leave you outside the meeting. So you should use the official way of joining these meetings. Okay. Let us start with our lecture. Right. So yesterday we spoke quite extensively on the limits. How do we evaluate the limits? How do we do direct substitution, and so on and so on? We did a number of examples. Oh, sorry. See. These people. Yeah, I was saying that yesterday we discussed quite extensively on how to determine the limits. And the main things that we realized is that the limit of f of x when x is approaching a is not always equal to f of a. So before we do direct substitution, we first check whether the number we are approaching is in the domain of our function or not. If it is not in the domain of our function, what we do is to rewrite the given function in such a way that it gives us a new function. For instance, in this example, we had this function, then we transformed it into this function whose limit when x is approaching square root of 3 was found to be equal to the limit of the original function. So that's what we did yesterday. So today we would like to move on and look at what we call the squeeze theorem, which help us to evaluate limits which may not necessarily be evaluated using the method we looked at yesterday. So this is the squeeze theorem. Squeeze theorem simply tells us that if we have three functions, say you have a function f of x, as you can see, we have a function f of x here. And this function is less or equal to another function g of x. And this function is less or equal to another function called h of x. So this g of x is squeezed between f of x and h of x. So if we have a function like this, then we may be able to evaluate the limit of g of x based on the limit of f of x and the limit of h of x as x is approaching a certain number, say a. For as we are indicating here, you can see the limit of f of x when x is approaching a. If it is equal to L and the limit of h of x when x is approaching a is also equal to L, then we can conclude that the limit of g of x when x is approaching a is also equal to L, even if we do not know how to evaluate the limit of g of x as x approach a. So graphically, this is what we have. We have our function h of x, our function g of x, and our function of fx. G of x lies between h of x and f of x. So we can evaluate the limit of g of x as x approach a by just comparing the limit of h of x as x approach a with the limit of f of x when x is approaching a. If they are equal, then we conclude that even the limit of g of x will be the same as what we got from these two. That's what we are saying up there. That's what we are saying up there. Okay. People are okay. Okay. Kopana, Mamhlade, do you want to say something? Okay, nothing. So we have a very important, okay, before that theorem, we have this example where now they are saying, show that the limit of x squared multiplied by sine of 1 over x as x approaches 0 is equal to 0. We want to show that. So it is not just saying you take 0, you multiply by sine of 1 over 0, then you get 0. Because if you do direct substitution, direct substitution will kind of allow you, or it will make you think that 0 multiplied by sine 1 over 0 is equal to 0. And this is meaningless, okay? This is meaningless because it is like a person who is saying 0 multiplied by infinity is equal to 0. This is meaningless. Okay, we will explain as we move on. But for now, just take it that it is meaningless to say 0 times infinity is equal to 0. So in this case, we note that we are unable to evaluate this limit directly, but we make use of what we know about sign of any number, any real number. If you take the sign of any real number, what we are saying is that if you have a sign, say, of theta, where this theta is an element of R, then the result here, the result for finding the sign, you can try it on the calculator. If you put your calculator on radian mode, you will observe that the sign of any real number, will lie between -1 and 1. That's something which it's known. So we are making use of that, and we say, okay, since we are talking of a real number, we expect sine of 1 over x to be a real number. In fact, yes, it is a real number, because when we are evaluating the limit, we will never reach 0. Okay? So when we say limit of sine of 1 over x as x approaches 0, we are safe because we know we are not going to divide by 0 in any way whatsoever, because we will never reach 0. We will never reach 0. We are just getting very close to 0. All right. So that is very important for you to understand. Now, we make use of the fact that the sign of any real number lies between -1 and 1. And we write what we have here. We write what we have, that, okay, then it means if we have any number, any real number, then its sign, the sign of that number, which is just 1 over x, then any number which is not equal to 0. Because of that, this result will lie between -1 and 1. Okay, so then the other thing that we've already discussed with our preliminaries, we noted that if you have an inequality and you multiply by a positive number, then that inequality will not change. And again, since we are working with real numbers, we know that if you take a real number, you square it, it is always positive, except when that number is 0. So x squared is always greater than 0 for all x. So you can multiply both sides of the inequality by x squared, and the inequality will not change. So we started off with this inequality. We are multiplying by x squared, which is always greater than 0, greater or equal to 0, or positive for that matter. We multiply minus 1 by x squared will be minus x squared less or equal to. We multiply sine of 1 over x by x squared, which will be x squared sine of 1 over x squared. And then this will still be less or equal to x squared, because we're multiplying throughout by x squared, like that. After doing that, it is giving us this kind of a situation. In other words, we will talk of the limit of x squared as x approaches 0, and the limit of minus x squared as x approaches 0. This is just the graph of the function under consideration. This is the graph of our function under consideration. So the limit of x squared as x approaches 0 is just 0, and the limit of minus x squared when x is approaching 0 is again equal to 0. Now, this minus x squared and x squared, as you can see, are squeezing x squared sine 1 over x between them. So it is in between this graph. It's in between this one and that one. Okay. So since we have that, taking f of x to be minus x squared from our theorem up there, g of x, which is in between the other two graphs, to be this, h of x to be x squared in the squeeze theorem, we obtain that the function which is squeezed between x squared and minus x squared, whose limits are 0 when we're approaching 0, must also be equal to 0. The limit of this function must also be equal to 0. That is the one example which illustrates how we can use squeeze theorem. Now, we have this important result which we are going to prove. I will prove it using theta instead of x. Let us use theta instead of x. Let us use, that is not okay. Let us just write it properly. So we want to show that, we want to prove that the limit of sine theta over theta when theta is approaching 0 equal to 1 geometrically. I want to prove this geometrically. So how do we do that? We consider a unit quarter second. The unit quarter second. What do we mean by that? We are looking at a quarter circle, a circle which is lying in the first quadrant. whose radius it's 1. Whose radius it's 1. So this is the portion of our second. The radius it's 1. The radius is 1. So let us draw some triangles. Let us say this is the hypotenuse, then it goes. Let us draw a right angled triangle. Let me use the red color. The red color, like this. Let us take which one will be visible. Maybe this is visible. Let us draw like that. And then take another one. Let us this is 90 degrees. Our angle here is theta. There you are. Then the radius is sorry, is 1 unit. The radius is 1 unit. So let us name this O, this A, B, C. Just also say this is D, for that matter. Then don't forget the radius, it's 1 unit. R is equal to 1. So you will note that if maybe we look at triangle OBC, which is a right-angled triangle, and we speak of BC divided by OC, this is tangent of theta. This is tangent of theta. But OC is the radius of our second, which is 1 unit. So it means BC is just tan theta. So we can write BC here to be tan theta, like that. So again, if we look at triangle OAD, in triangle OAD, you will note that if you take AD, you divide it by OA, this is opposite over hypotenuse, this is sine theta, but OA is the radius, which is 1 unit, therefore AD is sine theta. So this is sine theta, like that. Now, with this information, we have the following. We have the following. Let us look at these triangles. You will note that if you talk of the area, say triangle, let me call it OAC, is smaller than the area of sector OAC, which is smaller, is contained in the area triangle OBC. Okay, then how do we find the area of a triangle, we know it's a half base multiplied by height. This is contained in a half r theta. This is contained in a half the base multiplied by height. And so if we're using this diagram, you will see that we've got 1/2 a triangle OAC. The base in this case is OC. OC is 1 unit because that is the radius. So, and then the height is sine theta. So we can use the inequalities, and then R is 1. There we are. And then half the base again is OC in this case, OC, which is 1, and then the height is tan theta. So half tan theta, like that. Tan theta. So from that, maybe we can rewrite this like sine theta over 2 less equal to theta over 2 less equal to 1 over, no. Let me not write it that way. Let me write it this way. We know that tan theta is sine theta over cos theta. So we have our 2 here. So in this arrangement, let us multiply throughout by 2 over sine theta. Let us multiply by 2 over sine theta. And then if you do that, you will see that we take 2 over sine theta, you multiply this with it, you will get a 1, which is less equal to, you multiply by theta, 2 over theta, 2 and 2 will cancel, we are left with theta over sine theta, less equal to, you multiply by 2 over sine theta, 2 and 2 will cancel, sine theta and sine theta will cancel, and then we are left with 1 over cos theta, like that. And then now, there is something that you know, something that you know about inequalities, that if, say, for argument's sake, we say that let us see, what we know is that 1 over 2 is less than 1, and 1 over 2 at the same time, it's bigger than, say, 1 over 4. This is what we know. So if we invert this, you will see that if we take the reciprocal, we can say 4, it's bigger than 2, it's bigger than 1. So the same goes here. Take the reciprocal, it means if this 1 over cosine of theta is bigger than theta over sine theta is bigger than 1, then it means now we can say sine theta over theta less than 1, but greater than cos theta. And then we take the limit, we know that the limit of cos theta when theta is approaching 0 equal to, it's equal to 1, and the limit of 1 when theta is approaching 0 is still a 1. So this function is squeezed between a function whose limit when we are approaching 0 is 1 and another one whose limit when we're approaching 0 is 1. And that makes us conclude that by squeeze theorem, we conclude that the limit of sine theta over theta when theta is approaching 0 is also equal to 1. That is the result we are going to use. That's the result we are going to use. Okay. So we also have there are questions. Okay, let us hear the questions. Let us start with Makadzi Padziri.
Sir, I wanted to. Can you go back to the thingy? And I wanted to ask why you multiply by 2 over sine theta. Where is it coming from?
Where is it coming from?
Yeah.
Okay. We are simplifying, right? We realize that we have sine theta over 2. Can you see here? Sine theta over 2. Can you see this? Sine theta over 2. Hello? Yes, you can see it. And you can also see sine theta over 2 here. We just want to remove this sine theta over 2 throughout. How do we do that? We just multiply by its reciprocal. That's why. Okay. Probably are gone now. Can't hear you. And another question?
Sir, is there any other way to solve squeeze theorems without using a graph? Because the graph is kind of a little bit confusing.
This is what we are learning. This is what we are learning. You shouldn't fight to stay in in an environment where you feel you are familiar with this. There are other ways of course, we can prove this straight away using L'Hopital's rule and so on, but the main thing here is to train you to be able to prove things, to think logically. And because here we want to make use of the squeeze theorem to prove that which we've just proved. So there are certain things which you should not run away from. Even though maybe some people will say, no, you just know that it is 1, but sometimes we'll ask you to prove using this method. Of course, there are many methods of dealing with certain things, but if we are specific and we are asking you a question and we say use this particular method, you should be comfortable using that method that is being required. Okay, my father?
Sir, I can't see what you are teaching, sir.
Then what am I supposed to do to make you see? Let's help each other, because other than sharing what I have here, I don't know what else can I do to make you see.
You can just record what we are teaching right now, sir, so that we can be able to review what we are working on.
I think you are just, or you wanted to hear your own voice. Thank you. Okay, let us move on.
Sir.
Let us move on. Okay, then the next thing is for us to look at this corollary, that the limit of 1 minus cosine of x over x when x is approaching 0 equal to 0. So it's something which we need, something which we should know. And let us do it quickly. Proof. One way of looking at it is this. You have 1 minus the cosine of x over x. Let us multiply by 1, which will be given by 1 plus the cosine of x over 1 plus the cosine of x. This is equal to the limit. X is approaching 0, 1 minus cos squared of x. Sorry, we are not using theta here, we're using x. Let us use x over x into 1 plus the cosine of x, like that. So this is going to give us the limit. X is approaching 0. 1 minus cosine squared of x is sine squared of x. No, not theta, I want to use x. Not theta, I want to use x, like that, divided by x into 1 plus cosine of x. And this is going to give us the limit x approach 0 of sine x over x multiplied by sine x over 1 plus cosine of x. According to the limit laws, we have the limit x is approaching 0 of sine x over x multiplied by the limit when x is approaching 0 of sine x over 1 plus cos x. And we have just shown that the limit of sine x over x when x approaches 0 is 1. And then the limit of sine x over 1 plus cos x is 0 over 2, which is 0. So we are saying that the limit of 1 minus cosine of x over x when x is approaching 0 is equal to 0. Let us take some examples. there is one example which I want us to look at. Where is it? X cot 3x, okay? Examples. So usually we ask you to use, we say, use the fact that the limit of sine theta over theta when theta is approaching 0 equal to 1. And then to evaluate the following, we want to evaluate, let us say, to evaluate, let us say, the limit, I think is x cot 3x when x is approaching 0. Yes, x cot 3x when x is approaching 0. So the first thing again is to observe that 0 is not in the domain of our function, because if you speak of the cotangent of 0, cotangent is the cosine divided by sine, and the sine of 0 is 0, so we'll be forced to divide by 0. And then we'll get something which is meaningless. Therefore, 0 is not in the domain of this function. And we have to rewrite this argument or this function in another way. So we can say this is equal to the limit x is approaching 0. We want to make use of this fact here. And then we have x. Cotangent, we said, is cosine of 3x over sine 3x, like that. So this is going to be equal to the limit x is approaching 0 of x over sine 3x. If we are making use of limit loss, this will be multiplied by the limit of cosine of 3x. X is approaching 0, like that. And now, when we look at this, comparing it to that, or simply this, we will observe that here we have a 3, which we do not have here. So the argument of sine must be the same as what we have down there, or even up there. It doesn't really matter how you put it. Can be limit of what we're going to do is to rewrite this. So note that Okay, maybe I'll do it slowly so that you are able to see what is happening. So we want a 3 here. So we have x. Let us put a 3 which was not there. Divide by sine 3x. So we cannot say this is equal to that because originally we didn't have a 3 multiplying x. That is why we we balance everything. This is just a constant. So we have 1/3 there. Multiply now by the limit of cosine of 3x. X is approaching 0. And once we have this being equal to that, we know that this limit is equal to 1. So we just have 1/3 multiplied by the cosine of 0, it's 1. So it's 1/3 times 1, which is going to give us 1/3. And of course, it's easy to see the answer, but this is what we want you to do, the thinking. Let us take number A, this number A here. So you will see that this is equal to the limit x is approaching 0 of what? So in this case, we have a 5 here, we have a 2. We want a 2 down there. We want a 2 down there. So what we have is we have sine 2x. We want it to be 2x. Want it to be 2x so that we will be able to use this. But now, to do that, since we started off with a 5, maybe I can write it for you like this. You see, if that 5 is kept here, then it means we must have a 2 up there. Because 2 times 2, it's 1. 5 times x would be 5. So this and that are the same. And now 2/5, it's a constant. 2/5 is a constant multiplied by the limit of sine 2x over 2x. X is approaching, in this case, 0. Now, when it is like this, because this is 0, 0/0, the limit here is 1, according to our theorem. Therefore, we conclude that the answer is 2/5. Like that. Okay. 12:46, we are almost there. Maybe I should give you a chance to ask questions. If there are questions, let us go back to what we were discussing. In the absence of questions, I will do the next example. We've already done number B. Yes, Ogundipe. Correct.
Yes, sir. Good afternoon, sir.
Good afternoon.
Sir, may you please explain where you got the 2/5 from again, please?
Oh, okay. No. Okay. So what we have here, we have sine of 2x over 5x, okay? But the theorem tells us that the argument of a sine should be the same as our denominator there, okay? So in this case, we've got sine of 2x over 5x. 5x and 2x are not the same. That's the first thing we observe. So I said we want to write this expression like sine of 2x over 2x. But the moment I write sine of 2x over 2x, I will have introduced something which was not there originally, which is a 2. So in order for me to account for these 2, it's just like multiplying by 1. So 2 over 2, we are multiplying by 2 over 2. See, if you multiply by 2 over 2, it's just 1. The 5 was originally there. We just made use of the fact that multiplication is commutative. If you have A times B, is the same thing as B times A. In other words, if since I have here, you see, sine of 2x over 5x, I am multiplying by 2 over 2. So if I multiply by 2 over 2, then I can rewrite this as 2 sine 2x divided by, and then we swap the positions of 2 and 5. 5 comes this side, 2 comes this side. I hope it makes sense. So this 2 over 5, that's where it comes from. Does it make sense?
Yes, sir. Thank you very much.
Okay. Maybe in the absence of questions, let us do the last one and then we'll call it a day. Let us do, okay, we've done 2 of them. Let me show you how to do number C, how to deal with number C quickly. Let's look at number C quickly. Of course, it's just that we want the thinking, but you can see the answer straight away. You look at it, you see the answer, but we don't want you to approach these problems that way. So number C is like this. We approach 0. We have sine of 4x over sine of 6x. And we might want to make use of our theorem. So this will be equal to the limit x is approaching 0. We want now sine of 4x. We want a 4x there multiplied by, we want a certain number there over sine 6x. Okay, so what we want is, for this, we want a 4x here. For this, we want a 6x up there. Then how do we, if I write 4x here and 6x here, it simply means I introduced something which was not there originally. See, 6 over 4 was not there originally. So we must multiply here by we multiply by 1. Let me put it that way. We multiply by 1. in such a way that maybe I should change the color. Let me give it a red color. This one of ours, we introduced 6 and 4, which were not there originally. So we want a 4 over 6. So this will cancel with that. That will cancel with that. X will cancel with X. And we are back here. Then we just apply now the limit loss 4 over 6. This is a constant. Limit X is approaching 0. Sine 4x over 4x times limit 6x over sine 6x. X is approaching 0. And once we have that, we know this is 1. This is also 1. So we're 4 over 6. Over 6 times 1. Times 1. Which is just 2 over 3. Like that. Okay. So our time is up. Our time is up. Thank you very much. As usual, we share these things. They are there on Moodle. I think the last 2 lectures are there on Moodle. They are YouTube videos. So you can also check after a few minutes. After this class, you can go to Teams and you will still find the recording if you are able to access that. But I am also sharing this as YouTube videos. So I did that yesterday. So please take this seriously, because we may not have time to go through this again physically. I don't know, because they are struggling with the timetable. But we hope they will sort out the timetable so that we have physical classes and also physical tutorials. And don't forget that on the 28th of February, we have plans to write a short test. So this is serious. All right.
Sir,
So, hello?
Sir,
Yes.
can you please share the slides for the past online classes?
They are there on Moodle. Do you know Moodle?
Yes.
Yeah, you go there, you will find it.
Okay.
Yeah, they are there. It's easy to download. Okay.
Sir,
Yes.
I
Yes.
was not able to review the answers after the quiz. I don't know what would have been the problem.
Even myself, I don't know. I don't know. There are certain things which I don't know, because I'm not a technical person. I'm just an end user like you. I don't know, but that's not important. That's not important. What is important is for you to know what we have been discussing this week, and to prove to us, should we write our test, that yes, you know. And that one was to help you also to be able to prove to yourself that you are able to log on to Moodle and work on the problems. That was the main idea. So if you still have a problem with Moodle, make sure you address that, because the next one, we are not going to compromise, or it will be serious. I'm serious. Yes, let us. Morudu, you want to say something? We are done. Mm-hmm.
Sir, of this
Yeah.
model, we really need a
Eh?
who's the class rep of this model?
We have not yet elected a class rep. Isn't that we were planning to do so this week? We will do so. Don't worry.
Okay.
Yeah.
Say,
Yes.
how to find the results of quiz?
Oh boy.
Like,
Probably if you log on to Moodle and you click on that thing where I think I've already hidden the quiz. Let me say, don't worry about that for now.
okay.
We will show you, or I will see what I can do. But don't worry. That one does not necessarily count as such. So thank you. Let us meet again on Monday. Let us meet again on Monday.
Meeting.
Stop.